aqueous reaction, right? It's acting as an acid. Now, we always start all of our problems off as if nothing has happened. We can have a bottle that sat on a table with an acid in it for 1,000 years. And if we wanted to solve a problem for it, we would assume nothing's happened yet. So we're going to start off and say we have none of either of those products. We don't have any hydronium. We don't have any azide. That's azide. So minus x plus x plus x. And I am fine if you are able to go straight to the equation from this. I don't need to see the rice table. I'm putting it there to help jar your memory as to how these problems are working. Okay? Questions so far? All right. So we're going to have 1.9 times 10 to the negative fifth is equal to x squared over 0.75. Now I'm dropping the minus x, as we will always do, because we're going to make the assumption that the value for x that we get is too small compared to the value of k, the original value of the concentration to matter. Okay. Can somebody tell me what you get for x?
0.0377.
What?
00377.
Everybody good with that? Confirm?
Yes.
Now, that will equal the hydronium ion concentration, which means all you need to do is take the negative log of that to find the pH. The pH is going to equal 2 point something, right?
Yep. 42.
2.42?
Yeah.
Okay. Everybody all right? Now, percent dissociation. Somebody tell me what we need to do that. Joe?
0.00377 divided by 0.75.
And what do we get?
0.503%.
503? Which is not very much, right? Hence why it's considered to be a weak acid. Now, make sure you have this work. You may not have the rice table, but make sure you have the equation and what I have in blue on paper someplace, because we're going to come back and revisit this several times. Okay, so think of this as kind of like our cornerstone. We're going to come back and make some comparisons to this original problem. Okay. Who's got questions on that? Okay, so that's our warm-up, right? That's. I think there was a question on the free response portion that had you do that exact same thing, right? It may have not asked for pH. I think it did ask for pH and then percent dissociation. Now, the first half of this unit with acids and bases that we did prior to winter break was focused on identifying acids and bases, defining them. You know, what are our conjugates? If you have a salt, is that compound going to be acidic or basic? Put it into water. We did calculations dealing with equilibrium, which was basically solely having an acid or a base, putting it in water, and finding out what the pH was. Relative to that right there. Okay? That was about the extent of the calculations that we did. About right? Now, in this, the second half of this unit, we build on this. We're not going to just have an acid or a base in water. We're going to have an acid with its conjugate in water. We'll have a base with its conjugate acid. We'll have an acid and mix it with a strong base and see what the result is. What we did in the first half of this unit, that was fundamental to being able to do all these things. Okay? The problems that we're going to be working, they're going to be a little more involved. Okay, you're going to have more steps and stuff, but it's nothing you haven't done before. You've done stoichiometry, right? And you've done equilibriums. You know how to calculate pH. So we're just going to build off and build on and put those things together a little bit more. Okay. So I'm going to stick with the 0.75 molars hydrozoic acid. We're going to mix it. So I got 0.75 molar hydrozoic acid, but it's mixed with 0.75 molar sodium azide. So over here, if I were to draw a picture of this, basically we would have a beaker with a solution that's 0.75 molar HN3. Over here, we got a beaker that's 0.75 molar HN3 and 0.75 molar NaN3. I want to know the pH. And I want to know what's the percent dissociation. What equation do I use? What chemical equation do I want? Joe?
The NaN3.
Okay. What's the equation I want to use then? What's the chemical equation? If you're going to use the NaNO3 or NaN3.
It's not in water, is it?
Yeah.
It is.
See my beaker?
So NaN3 plus H2O to N3, or not N3, plus, wait. NaOH plus HN3.
I'm going to change it, modify it just slightly. It's not wrong, but you got a strong base in there, right? Which if you had a strong base in there, would that reaction even take place? What do we do whenever we see sodium? What do we do whenever we see potassium?
So would it just be N3 plus H2O to OH plus HN3?
The only thing I want to have you add is that you would put a charge on it. Now that looks better. So this is a salt, right? Remember, when we have a salt, we want to look at the part that's going to interact with the water only and ignore anything else. So this is a salt that comes from a strong base, sodium hydroxide, and a weak acid, hydrozoic acid. The N3 part, that is our focus for that equilibrium. But is this the equation we have to use? Is there another equation we could use? Zoe?
Could you do N3 minus plus HN3 to HN3 plus N3 minus?
It's a valid equation, but not the one we want to use. So, because they're conjugates of each other, we're not going to think of the acid and base as reacting with each other to neutralize. Because that's the equation. That's why I said it's a valid equation. You do have an acid and a base, they neutralize each other. But when they're conjugates of each other, we don't want to look at it that way. Okay? You guys are missing the obvious one. Max?
Is it NaOH plus HN3 to NaN3 plus H2O?
But there's no sodium hydroxide anywhere. Zoe?
Can you just flip the equation around? So HN3 plus H2O to the other part of it.
That?
Yeah.
Which is what? Class. Look over there.
Same thing.
Now, we can use either one. Which one do we want to use? Why?
We already did it.
Easier.
We already got the Ka value, right?
Yeah.
To use the, okay, so this equation right here, you could use. We could use either one of these. It's what information. One of the things, some of these problems are going to get long, okay? It's not that they're overly challenging, it's just there are a lot of things you may need to do to complete it. You want to try to pick the route that's going to give you the least amount of work that you have to do. If we were going to use this equation, what would we need to be able to do this equation?
KB.
KB, because this is acting as a base here, right? The N3. So we would need a KB. Can we find the Kp for this? Well, good luck. But do I have a K? I would need to find it from what?
That's dumb.
The Ka over there, right?
Yeah.
I had to do that Kw is Ka times Kb. Remember that equation?
Yeah.
Whereas if we use this equation, we already have the Ka for it. Everybody good? Okay, so how much H in 3? 0.75. Now remember, nothing's happened, right? So how much hydronium? How much azide?
0.
0.75.
0.75. Right? Now remember, I don't think, did we answer what do we do with sodiums and potassiums? Get rid of them. We don't want this, so that it's just that's our key. Okay, so before any reactions have taken place, I've got 0.75 molar of the hydroxylic acid, and I got 0.75 molar of the azide. Minus x, plus x, plus x, 0.75 plus x, x, 0.75 minus x. So we plug in. So 1.9 times 10 to the negative fifth equals x 0.75 plus x 0.75 minus x. Joe?
You said the minus and plus x's were too small to matter.
Good. Anytime you get plus or minus x, okay? Drop them. So we're going to say close enough to being equal to x times 0.75 over 0.75. I want to see if anybody picks a calculator up. Nobody want? You want to do Austin, you want to do calculator? X is equal to what?
1.9 times 10 to the negative 5.
Now, class, something I want you to understand here is that that's not always going to be the case. It is because I made the two concentrations equal. Right? If I didn't make them equal, you'd have some math to go through and do. Hopefully not too challenging. What's the pH? Because this is equal to the hydronium ion concentration.
4.72.
4 point what? 2?
72.
Okay. What's the percent dissociation? How do I find it? And what do you get?
.0025%.
On what?
0025.
Now remember how I said this is kind of like our cornerstone, and we're going to come back to it? Let's make some comparisons here. I have the same concentration of acid. In this one, I only have acid. On the right-hand side, I have an acid mixed with its conjugate base. And look at, we have some very significant changes here, right? percent dissociation, although it's very small here, was 200 times greater percentage-wise. We've gone from 0.5 down to 0.0025%. Our pH went from, if it's just the acid, 2.42. If it's mixed with the acid and the base, it went up to 4.72. Why did it go up? Why did pH go up? There's a couple of ways of thinking. Andrew?
You added a base, so it's less acidic.
You added a base. So if I had this solution over here, I've started with this, and I added azide, that's a base. This is where I go, Zoe, where it's kind of like what you were saying. Your acid and base are going to neutralize. The reason why we don't use that equation is because we don't have the water involved, which is what's giving us our equilibrium part. So if I were to start adding a base, it doesn't matter, any base. If I start adding a base to this, pH has to go up. There's another way of thinking about it. If I increase this amount, this azide, if I increase this, what's going to happen to the equilibrium? What did you say?
The equilibrium would not be equal anymore.
You're right. Which way? So what's going to happen? If I increase the amount of azide, this goes up. It's got to shift, right?
When you think about static shock,
I should say. It's got to shift, correct?
Yeah.
Which way?
Backwards.
Backwards. It's going to go this way. So if I increase this and it shifts that way, class, what happens to this? It's got to go down because you're going that way, right?
Yeah.
And this is what's telling you the pH.
True.
If this goes down, if this decreases, you're getting less acidic. So there's a couple ways you can look at it. You can look at it as you're adding a base, which is kind of neutralizing the acid, even though they're conjugates of each other. Or you can look at it as an equilibrium and say, you're adding a product that's going to cause the reaction to shift towards the reactants and decrease the amount of hydronium. Either way is correct.
balance of positive and negative.
Or another way is saying, if you add this, it's going to react with the HNO3 to neutralize, to give you the, and going back to your equations though, the reason why we would choose this is because this is the stronger acid than this is. So if I add this to the water, it's going to react with this hydronium before it reacts with its conjugate. Questions? Be all right? What's stronger? Azide as a base or hydrozoic acid as an acid? What's stronger? The acid or the conjugate base?
Yes.
Why?
Because it's more acidic than this basic.
When? What? Well, if I have these both mixed together equally, I get equal amounts, right?
Yeah.
What's the pH? It's acidic.
So when it's at equilibrium, or when they're equal amounts.
They're equal amounts. Okay? When they're equal amounts, you can make that comparison. Now, we could also go back and simply look at the K values. We got the K value for the Ka for our hydrozoic acid. What is the Kb value for the N3? So we take 1 times 10 to the negative 14th divided by 1.9 times 10 to the negative 5th.
5.26 times 10 to the negative 10.
Negative 10?
Yep.
Okay. So look at the K values. 10 to the negative 5th versus K to the negative 10. The acid is going to be it's going to be stronger as an acid. The conjugate acid is stronger than the base. So if you did have equal amounts of both of them, you would be able to have an acidic solution. Questions? Could we mix sodium azide with hydrozoic acid in such a way to make the solution basic?
Yes.
What would we have to have?
A lot of concentration of base.
A higher concentration of the base. Enough so that we would shift that to be acidic. Okay. If you want any pictures of that, I'm going to leave this up because we're going to come back to it. If you want any pictures of that, take them down because I'm going to go and erase it. You have 5, 4, 3, 2, 1. I'm erasing.
Yeah, I always think there's a smart call. All right, determine the pH of that solution. Yes, you have to. Yes, it's required. The pH? It's going to be 7.455.
7.46, Austin.
K. Maxwell.
Oh, I guess it's
That's a -8.
All right, I'm going to show you. I'm going to show you the long way, and I'm going to show you the short way.
Except you waste more time.
Yeah, they're not always going to be.
Okay, but they are, so.
Yeah, Joe, take as many shortcuts as you're given. There's not.
Swing, did you memorize that equation sheet you made?
And remember, drop that sodium, right?
Although I still have it.
Drop it like a bad habit.
So.
Core 6.
Thank you. Everybody all right? Oh, well, that's the thing. So good question, because this goes back to the question I asked in the previous problem. What's the stronger in this situation?
The base.
The acid or the base? Base. So the conjugate base is stronger as a base than the acid is as an acid. That's what. Now, this pH is above 7 because we have the conjugate base. If we did not have this, if I did not have this, if I just had 0.5 molar hypochlorous acid in water, remember, we wouldn't have this. This would be 0 here, right? This would be acidic. Okay? So if you have a weak acid, and that's the only thing you have in the solution, just the acid, then it's going to be acidic. It's when you get its conjugate base mixed in there with it that it could be a basic solution, depending on what the strength of that conjugate base is. Now in this case, we can say that the base is stronger as a base because we have, again, equal amounts of these two. If we did not have equal amounts of them, that would be a little more challenging. Or we could look at our K values. What K value would be the tipping point between being a weaker acid or a stronger, or a weaker acid or a weaker base? Or stronger acid, stronger, however you want to say it. Andrew?
10 to the negative 7.
10 to the negative 7. The K value for this acid is 10 to the negative 8, right? What's special about 10 to the negative 7? That's when, you know, water, that's the, remember the KW for water is 1 times 10 to the negative 14, right? And Ka times Kb is equal to 1 times 10 to the negative 14. The only time that you could have an acid and a base equal to each other in their strength would be if their K values were 1 times 10 to the negative 7. And you're thinking, well, that would be water, Mr. K. No, Kw for water is 1 times 10 to the negative 14. Okay. Who's got questions about this work?
Okay, but how does that happen? What's going on with that? Okay, what
The previous problem and this problem both are what we would consider to be a buffer solution. Now, chapter 14 is the chapter that we're dealing with these problems. And the thing about chapter 14 is that it's a lot of this type of stuff. I'm going to tell you to read it. It's important that you do so, okay? But it's a lot of the math in describing stuff. It's actually, there's more examples in the problems than there are text. But the text part is really, really important. So, a buffer solution is a solution that resists changes in pH. And a buffer solution is also going to be made up of a weak acid and a weak base mixed together. So a buffer solution is a weak acid and a weak base mixed together. And when you have weak acids and weak bases mixed together, those solutions will resist changes in pH. Now, there's certain things about buffer solutions that make buffer solutions better or worse. Ideally, you want a buffer solution that's made up of the conjugate acid and base pair. We'll talk more about those details later. But it doesn't have to be. You don't have to have conjugates of each other to be a buffer solution. It depends on what you need to do. Now, for what we are going to do in the problems that you're going to see, we will only be dealing with buffer solutions that are made up of conjugates of each other. If they're mixtures of different things, then that becomes a little bit of a challenge. The reason why we can do this problem here is because they are conjugates. If I had this as a different weak base, then this K value we're using would not be valid. That's why our focus is going to be on equilibriums of buffers that are conjugates of each other. I'm not saying that you can't do that. I'm just saying our focus is going to be on those. So again, a buffer solution is a mixture of a weak acid and a weak base, preferably conjugates. And those solutions will resist changes in pH. Now, in the two problems that I gave you, this one and the previous one, we have a special circumstance. Austin, why did you know what the pH was going to be so quickly?
Because the Ka value will be the hydronium value for the second equation.
And when is that going to be true?
When the molarity, or just the amounts of each solution is the same.
So the concentration of your acid is equal to the concentration of the conjugate base. Or if we were dealing with a basic solution, the same basic principles apply. If I had a base and I had the conjugate acid, this is what we call the 1/2 equivalence point. Now, technically, we need to do some other thing that I'm not going to describe yet to technically call it a half equivalence. But the thing that is true at the half equivalence point, when we get to the true definition of what 1/2 equivalence is, you'll understand why it's so important. But the thing that is true is that the conjugates of each other are equal. That's key. This will save you lots of time. It will make certain problems so much easier. one of the things that we can say at the 1/2 equivalence point is that the concentration, or your K value, your Ka, will equal your hydronium. Your Kb will equal what? Now, something we haven't done much of, but you are going to start seeing a lot more of, is pK values. What's P mean? Negative what? No. Different symbols, different classes. You're right. P does mean percent in some cases. It means it's another thing in statistics. Who's in statistics? Joe. P values. You've done those, right?
Yeah.
They tell you how accurate it is. I can't remember.
I don't know if we've done them. We just use P for probability.
Oh, okay. There's another P value for that. They read a lot of letters in statistics. So P for us means negative log. So if I have the pK value, that's the negative log of the K value. So if I were to take the negative log of this equation right here, I would have the pKa is going to equal the negative log of this is called what? pH. So if you had a problem presented to you and you had both of these, you saw, oh, these are equal. Do we want to know the pH? Do you need to do any of this? No. You just go straight and say, what's the K value? And take the negative log of it. Even better, many times the K value would not be given to you as a K value. It'll be given to you as a pK value. It says, so you could have a problem presented to you, said the pK value is 7.46. What's the pH when the concentration of these two are equal? Oh, that's easy. 7.46. If you're dealing with a base, same basic idea. pKb would equal pOH. You got to be careful, right? You got to recognize what you're dealing with. Good. Was that first bell ring at 50? Okay.
For us, yeah.
Yeah. Did she clear it up for you? Who's got questions up here? All right. It's 0.5 molar hypochlorous acid and 0.35 molar sodium hypochlorite. What do we need to change? Actually, just do it. Find the pH. And you can't do this, right? Because why?
The
Concentrations aren't the same. Go. Find the pH of a solution that is 0.5 molar hypochlorous acid and 0.35 molar sodium hypochlorite.
Oh, wait.
You're upside down.
Yeah. So it should be 35 divided by
So you're so
Have equivalence is when the concentration of your conjugates are equal. Hang on to that question. Because we have to, we're going to do what's called titration. What's that? Well, they're not overly hard, they're just a lot of work. So much so that Austin might have to actually write something down. Come on. What's the matter? pH. That was
That's what we thought of.
Zoe?
Why do you have it as x minus 0.5 and not 0.5 minus 0.5? It's also in the other equation.
Oh, yeah, because that doesn't work out, right? Thanks. What's x equal to? 5 even? pH? What?
7.3.
Is it 3 0?
No, so that's
701.
So yes. Okay, now, in the previous question, we had equal amounts, correct?
Yeah.
In this question, we've got less of the base, and it's still basic, right? Again, so this is illustrating again that base, the conjugate base of hypochlorous acid, is stronger than what the hypochlorous acid is. Now, what was the pH of the previous problem? 7.46? And this is 7.30. This is kind of an illustration of a buffer. Buffers are designed, or buffers, we use them purposefully and naturally to resist changes in pH. Okay, that was part of the definition I gave you. It's a mixture of a conjugate acid and base, or I'm sorry, a weak acid with a weak base that resists changes in pH. And you can see here that by reducing the amount of the conjugate base, did we get a drastic change in our pH? No. This is why or how a buffer is going to work. If I add an acid to a buffer solution, the acid will react with the what in that solution? Four letters.
Water. Never mind.
Water. W-A-T. Oh yeah, if you spell it W-A-T-R, four letters. Abbreviations. Water. Water. If I add an acid to this solution, what is it going to react with in that solution? The base. So if I react it with the base, I'm going to take the base away, right? And vice versa. Well, actually going back to this. If I take this away, even if I take some of it away, my pH isn't going to change a whole lot. Okay. Okay. Now, what seven? What? Did I do something wrong?
No, I was just going to ask a question.
Go ahead.
Are we ever going to have equations where the initial value for hydronium is not 0?
No. And that's actually a really good question because we always default to that nothing has happened. So all of our problems are going to end with an equilibrium of some sort. And that equilibrium is always with water, for what we're doing. And because we're assuming that no reactions occurred with the water yet, we don't have any hydronium hydroxide to start with. Now, could you get to the same result if you did take into consideration what the actual concentrations of water and hydroxide, hydronium hydroxide are? And the answer to that is yes. You probably get a little bit more accurate answer, but it becomes much more challenging in terms of the work that has to be done to do it. Okay. We got 1 liter, 0.75 molar hydrozoic acid. It has 0.2 moles, not molar, 0.2 moles of sodium hydroxide added to it. determine the pH after adding the sodium hydroxide. First off, what is hydrozoic acid? What do we classify it as? It's a weak acid. What is sodium hydroxide? Strong base. Okay? Strong bases and strong acids, but since we're dealing with the base here, strong bases do what? They react completely. So when we add this 0.2 moles of sodium hydroxide, it's going to react completely. What is it going to react completely with? The acid. Not water, the acid. The reason why it's going to react with the acid is because the acid is going to be stronger as an acid than water is. I'm sorry, yeah, water is as an acid. Remember, water is an acid and a base. Okay, it can either accept or it can donate. So, if we are adding a strong acid or strong base to a solution, and these are really the only types of problems we're going to look at. We're not going to look at adding weak acid to weak bases. I'm not saying you couldn't do it, it's just not a focus of what we want to do. Okay? So, these problems have to be done in two parts. You have the stoichiometry of the reaction between the strong and the weak. And then you have the resulting equilibrium from what's left. Okay? Now, I tried to make this one as simple and straightforward as possible by giving you, we need to know the volume of this. We haven't used the volume for a long time, because our equilibriums are all just based on concentration. It doesn't matter if you have 10 million gallons of it or you have a millionth of a milliliter. The equilibrium process is still done the same way. It's concentration based. But we have to do stoichiometry here. This is going to react completely with any of this acid that we have in the solution. So the reaction is going to be HN3 plus what? What's that?
OH minus.
Good. Because what do we do with sodiums and sodiums and potassiums? Get rid of them. It's not the sodium making the sodium hydroxide strong, it's the hydroxide making the hydroxide strong. Single arrow. Why?
Because it reacts completely.
Completion. There's no equilibrium. You're going to make what? Now, this is going back a ways, but rice tables can be done using what units? Moles, which we haven't done. We're going to. Molarity and no grams, ever. Grams are useless to us.
ATMs.
Which is the pressure. Pressure. Okay? Now, when we're doing stoichiometry, we want to do the rice table in moles. Because we're looking at how many particles are getting used up and stuff. So, I made this easy. If I've got 1 liter of 0.75 molar, how many moles do I have? 0.75 moles. I am putting a unit on this to distinguish what we have done and what we are doing now. How many moles of hydroxide? Well, how much? 0.2. You guys do see the 0.2 up there, right?
Yes.
I'm going to make this 0.20. 0 moles. What's the limiting reactant? Don't ask Siri, she's not going to know.
The hydroxide.
Who said that? Why the hydroxide?
Because it's gonna react completely.
And how many moles of it do you have?
0.2.
And how many moles of the acid do you have?
0.75.
You didn't say it loud enough.
What the heck?
I didn't hear you.
My bad. I'll be louder.
Okay.
Please.
I mean, that's not hard for you. You are
It
allowed
really
that.
isn't. I could definitely be louder. It's all day.
You guys haven't gone back to being afraid of giving the wrong answer.
I always get wrong.
I said water.
I only get on.
Yeah.
Okay, now,
Yeah.
so if you remember back, I know it's been a while. It may be, you know, we haven't done limiting and excess reactant problems in quite some time, but the basic fundamentals are still there. You're going to run out of something, right? I've always given thought to introducing rice tables with this, doing limiting and excess reactants in first year in chemistry, because it does make it simple. Actually, simpler because everything here is 1-to-1 ratios. Okay. Now, the only thing I would caution you about is that this was 0.20 for the hydroxide because it was sodium hydroxide. If this was calcium hydroxide, if I had 0.2 moles of calcium hydroxide, now it would be what?
0.4.
It'd be 0.4 because there's 2 hydroxides for every 1 calcium hydroxide. That's it. I'm not saying that that's something that's going would occur frequently. It's something I want you to be aware of in case. Okay? Now, we know that this is going to react completely. So if this is our limiting reactant, it's all going to go away. In this rice table, we know the change. We're using the rice table to tell us what are we going to end with. Is everybody okay? All right? Now, what's the problem now? What unit do we have? We got the unit of moles. And we've got, what's left behind now is a weak acid and its conjugate base, which means we have an equilibrium we need to deal with. And equilibriums are done in what units? Molarity and pressures. So I'm finally going to erase this board. I shouldn't erase all of it. I don't know. Now, the thing, excuse me, the thing that we're making an assumption about over here is that the addition of that sodium hydroxide doesn't change this volume. Most of the problems that you're going to encounter, you would be told either any change in volume is negligible or ignore any volume changes, or the addition of the solid doesn't change the volume. The other thing that you need to be careful about is what this volume is. I made it relatively easy so that when you say, if I've got 0.75 molar, if it's a liter, I got 0.75 moles. If this is not 1 liter, you need to go through and do some math, right? Now, we've got 0.55 moles of hydrozoic acid, correct? But what's the molarity? What's that? It was 0.75, but we've reacted some of it with the base. 0.55, why?
Because it reacted.
But why is it going to be 0.55?
You have to subtract the 20 OH.
Okay, so you got 0.55 moles. Why is it 0.55 molar?
Oh, because it's 1 liter of solution.
Because it's 1 liter of solution. If it wasn't 1 liter of solution, what would you be doing here, people? Dividing it by that volume in liters. Okay? So, it is 0.55 molar, 0, and 0.20 molar. Everybody good? Now, minus x, plus x, plus x. 0.20 plus x, x, 0.55 minus x, 1.9 times 10 to the negative fifth equal to x times 0.20. I'm going to go ahead and just drop them. You got it, Joe?
Yeah, 5.23 times 10 to the negative fifth.
Confirm or deny?
Probably.
Don't tell me probably. Is that a confirmation? Okay. Now that's going to equal the hydronium ion concentration, and since we want to know the pH, that's going to be 4 point what?
2.8.
28? So go back to the very first problem we did today. And what was the pH of a solution that's just 0.75 molar hydrozoic acid?
2.42.
How much?
2.42.
2.42? And we added sodium hydroxide to that solution. And it went up almost 2 pH points, right? That's because we added the sodium hydroxide to just an acid. This was not a buffer. There wasn't anything there to help protect the change in pH. Everybody with me on that? That's where we're going to start off next time. I'm stopping a little early, but that's all right.